One token ID goes in, one vector comes out, a fixed-width row of numbers the model can use. The ID deserves some suspicion. A tokenizer assigns each token an integer, but that integer is only an arbitrary index. Two IDs that are numerically close are not close in meaning. The number marks a position in a list. It measures nothing. So where does the vector come from? Picture a table, one row for every entry in the model's vocabulary and every row the same width, one column per embedding dimension. This grid is the embedding matrix. Its two sizes are separate architecture choices. The row count is the vocabulary size, while the column width is the embedding width. Now the lookup. The token ID works like a catalog number. It retrieves one record, one highlighted row, and its digits tell you nothing about what that row contains. That is the entire analogy. Literally, the model performs an indexed lookup in a trainable matrix. Nothing is calculated from the ID's magnitude. The ID only points. This row, not that one. The selected row is the vector. Why store rows at all? One alternative represents a token with a vector as wide as the whole vocabulary, all zeros except a single one at the token's position. That one hot vector is sparse and vocabulary width. The embedding row is a learned dense alternative, fixed width with each slot holding a value that training can adjust. Every token therefore leaves the lookup with the same embedding width ready to enter the next stage. Entries are model parameters. They can be initialized without useful structure, then adjusted through backpropagation along with other weights. Across many updates, relationships between rows that help the model's task can emerge. Nobody needs to name the columns or assign one human-readable meaning to each dimension. The useful structure is learned. But lookup creates an important limit. Inside a given embedding table, the same ID selects the same starting row. The same token in two different sentences therefore begins from the same token vector. This input embedding cannot be the token's finished in-context meaning. It is a learned starting point before the network uses position and surrounding context. Token lookup alone also contains no order. The original transformer added fixed sinusoidal positional encodings to its input embeddings and tested learned encodings as well. Early GPT used learned position encodings in its initial representation. Other architectures can encode position differently. The safe principle is that the model must incorporate information about where tokens occur. The lookup row alone does not provide it. So keep four things distinct. The token ID is an arbitrary index. The input embedding is the learned row that ID selects. Position information tells the model where the token occurs, and the contextual representation is what later transformer blocks produce as they transform the starting vectors, using the surrounding sequence. That final transformation is the part we have not opened yet. What does a hidden layer actually do to a vector?